Hello and welcome to a new video on cryptography for everybody. In today's video, we will have a look at Trivium. Trivium is a stream cipher and is part of the portfolio of the Estream Project. I structured this video into 5 different parts. In the first part, I will introduce you to the Estream Project. After that, we will have an introduction to Trivium, followed by a single round of Trivium, and then the initialization of the cipher. And finally, of course, we will do it in CrypTool 2. We will encrypt and decrypt using the Trivium cipher. When you search for Trivium, you usually will find this drawing here, and this drawing here is from Wikipedia. As you can see, Trivium is a cipher that looks like a circle, or the drawing looks like a circle, and the data will go round and round and round in the cipher. How this works we will see later in this video. The Estream Project. The project aim of Estream was to identify new stream ciphers. And it was organized by the encrypt network. encrypt stands for European Network of Excellence in Cryptology. First, there was a call for primitives, stream ciphers, that was issued in 2004. The project was completed then in 2008. And in this project, the ciphers fell into 2 profiles. There was the first profile, profile 1, which was that stream ciphers for software applications with high throughput requirements. And there was the second profile, profile 2, which was stream ciphers for hardware applications with restricted resources. Restricted resources here means limited storage, gate count, or power consumption. I have here a table of these 2 profiles, and these tables contain the final Estream portfolio as of 2011. In profile 1 we had HC128, Rabbit, Celsa 20/12, and Sozemanuk. In profile 2 we had Grain, Mickey, and Trivium. And Trivium is a cipher that we discuss in this video. What is Trivium? Trivium is a synchronous stream cipher. Synchronous here means that the key stream is generated independently of plain and ciphertext. It was created by Christophe de Cagnières and Bart Prinell. The key size of Trivium is 80-bit. And Trivium has an initialization vector as an input that has also a size of 80-bit. And the cipher generates up to 2 to the power of 64 bits of output. And it was a simplest Estream entrant. Trivium provides a trade-off between speed and gate count. In hardware, when you want to design Trivium, you only need about 3,488 logic gates. And the other trade-off part was that it was reasonably efficient in software implementation. And if you are further interested in more details on Trivium and its design, I suggest that you have a look at the paper of Cagnières and Prinell, Trivium in New Stream Cipher Designs from 2008. Let's have a look at a single round of Trivium. Trivium has a 288-bit internal state. The bits are numbered from S1 to S288, and you have 3 different sized shift registers. You can see the bits in the graph here on the right side. Here it starts with S1, then we have some bits, then we have S66 and so on. And this is the first shift register. Then we have a second shift register from S94 to S177. And we have a third shift register from S178 to S288. And as you can see, these shift registers are connected with some logic gates. How does this work? You can put this drawing here or this graph into equations, and in each round the cipher performs the following steps. It first computes intermediate values T1, T2, and T3. These are XOR combinations of different bits. Let's have a look at T1 for example. T1 is a XOR combination of S66 and S93. I only put the 0 here so that all the numbers here have the same size. So as I said, T1 is S66 XOR S93. How can we find this in the graph? Here we have S66 and we have S93. And this here is the XOR operation of these two bits. XOR means that the result is 1 if only one of the two bits is 1. If both of the bits are set to 0, the XOR here is 0, and if both of these bits are set to 1, then the XOR is also 0. And you can see here that the result of this operation here, of this XOR, is T1. For the second shift register, you have the same. We have also two bits, S162, XORed with S177. Then you get, as a result, T2. And for T3, for the third shift register, we have also an XOR combination of two bits. We have S243, this is this bit here, XORed with S288, this bit here. And then we have, as a result, T3. And then these three intermediate bits, T1, T2, and T3, are again XORed, and this is our output bit, and this is a bit for the stream of bits of the stream cipher. You can see the output bit here, and we have an XOR operation which takes T1, T2, and T3. XOR these all three, and we get an output bit. After obtaining the output bit, T1, T2, and T3 are further changed using different binary operations. For example, T1 now gets T1 XOR, and then here we have bit S91 and bit S92, and again an XOR with a bit S171. So what does this AND here mean? AND means that these two bits have to be 1, and only if both are 1, then the AND of these two bits is 1. If only one of these two bits is 1, then the result is 0. And of course, if both of these are 0, the result of this term here is also 0. Where can we find this in our drawing here? When we have a look, we go from T1 to the next T1 step. Here we have our T1, and we go down to here. Here we can see the 91th bit and the 92nd bit, and these are combined using an AND operator. The result of these goes into this XOR. This is this XOR here. No, this is this XOR here with the T1. This part, T1 XOR this part. The result then is XORed again with an additional bit of the second shift register, S171. This is this part of the equation. And we get the green T1. Same as for T2, we also have an AND of two bits, XOR with the previous T2 value, and XOR with an additional bit from a shift register. Here we have the previous T2, it gets XORed with an AND value of 2 bits, and then the result is XORed with a bit with S264 from the third shift register. And with T3, we also have the same construction. We get the previous value of T3, we XOR it with an AND combination of 2 bits, here in this case S286 and 287, and then it is XORed also with a bit from the next shift register. In this case, we have to go to the first shift register. This is the first shift register. We take S69, this bit value here, and we XOR it with this value to get the T3 in green. Then we have a right shift of 1 of the state. That means that all the bits in the shift registers are shifted by 1 to the right. So the previous S1 is the next S2, the previous S94 is the next S95, and the previous S178 is the next S179. And of course, the bits following these bits are also shifted 1 to the right. The last bit of the state of this shift register then is omitted. So S93 is removed or falls out of the shift register, and S92 goes into S93. Here's the same. S177 goes out of the shift register, and S176 goes into S177, and the same in the last shift register. And then we take our previously computed green T1, T2, and T3 and put these back into the shift registers. T3 goes into the first shift register. The T1, the green here, goes into the second shift register, and the T2 goes in the third shift register. And now you can see why we have a circular structure here in the cipher. The bits always flow through the 3 shift registers, and one bit from the previous shift registers with combination of different other bits always go into the next shift register. When we have a look at this drawing here, which looks a little more complex, here we can see that we have this circular structure. This is basically the same as the drawing here. I personally prefer this drawing because here we can see that we have 3 shift registers and that each shift register is connected to the next one. And this is how one round or a single round of Trivium works. Now let's have a look how we add a key and an initialization vector into these states or shift registers. Here we have the initialization of the cipher. And the cipher is initialized in the following way. First, the key is written into bit 1 up to bit 80. This is S1 to S80. Then the initialization vector is written into bit 94 up to bit 173, also 80-bit. So the key and the IV both are 80-bit. If you don't know what an IV is, the initialization vector, this is not a secret, and this can be known to everyone intercepting encrypted messages of a cipher. The key has to be kept secret between the parties using the cipher. The IV is used that even if we use the same key on the same message, the IV is always chosen differently for each message. That means that even the same plaintext messages are encrypted differently, but the IV is not secret. Then, when we edit or put the key and the IV into our cipher, there's also a constant that has to be written into the cipher. And the constant is 0000111. This is 7, so this is 1, 2, and 4. This is the value 7. And this is written into bit 281 up to bit 288. So at the end of our shift registers, at the end of the third shift register. After we have written all these values into the shift registers, the cipher is executed exactly 1152 rounds. So we perform 1152 times this cipher here, this round of Trivium. And then finally, the first bit of the key stream that we actually use for encryption is the result of round 1153. So after 1152 initialization rounds, we obtain our key stream. And the key stream is a pseudo-random bit stream. And this pseudo-random bit stream then is used for plain and ciphertext, for encryption and decryption. And how do we do this with stream ciphers? We XOR onto the plaintext the key stream, then we get the ciphertext, and when we want to decrypt the ciphertext, we XOR the same key stream, because we use the same key and initialization vector, onto the ciphertext, and we get back our plaintext. Now that we know how Trivium actually works, let's encrypt and decrypt using the newly implemented Trivium cipher component of CrypTool 2. I'm here now in CrypTool 2 in the Start Center, and I want to show you how we can use the Trivium cipher. And first, we create a new workspace. In the new workspace, we search for Trivium. And we drag and drop the Trivium 2 times onto the workspace, since we want to encrypt and decrypt. I want to encrypt and decrypt text, so I need a text input for the plain text. And of course, we need to add a key and an initialization vector. and these will be biggest width. Then we have here key and IV. Clearly, the Trivium cipher works with an iCrypTool stream with binary data. So we have to convert from text to binary data. And of course, for key and IV, it wants 80-bit binary strings or 80-bit binary data. So we also have to convert. We convert by using a string encoder. Always wrong. A string decoder. And we connect the string decoder with the plaintext and then the stream output with the first trivium. Then we will have the second trivium here. We connect this because we want to encrypt and decrypt. And of course, we want to see the results. So we need some decoders, some encoders here. And we need 2 additional decoders for the key and for the initialization vector. Then we will align this on top. We connect the key input with the string decoder, this with the first trivium, this with the second trivium, and we do the same for the IV, and IV here, and IV there. Then I move this line here a little. Then we connect the output of the first trivium with this component here, and the output of the second trivium with this. And then we need text output. This here will be our cipher text. And then I copy this. And this here will be our decrypted plaintext. Now we have to set up all the components. I start with the decoder here. We want to enter arbitrary text, so text UTF-8 is fine. Then we want to enter the key in hexadecimal, so I change this to hexadecimal. And with the IV, I also change the second string decoder or the third string decoder here also to hexadecimal. Then the ciphertext will be arbitrary binary data, and when we print this out in a text output, we can't see anything, maybe only a few characters, but mostly we can't see anything. So we change this also to hexadecimal, the ciphertext. And the plaintext, again, should be UTF-8. Now we need a plaintext. This is hello world. This is the test of the Trivium cipher component of CryptTool 2 and a nice smiley. Then we need a key. 80-bit. When we enter this as a hexadecimal value, then, for instance, this here is 1 byte. So we need 10 of these to have 8 bytes and 80 bits. So we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 characters. And we change the key a little, that we have a more or less random key here. Looks not really random, but I think this is fine. Then we need the same. We need 20 characters for the IV. And what I do, I just go over these here, digits, and then put some character, some uppercase letters, A to F for hexadecimal values into the IV. Now we have here 10 byte key and 10 byte IV, which is both 80-bit. Now we have to change the trivium to, no, we don't have to change. It already has 1152 initialization rounds, and the second one has the same. Now let's test it. Let's press play. And as you can see, the Trivium cipher component, the first one, encrypts our ciphertext here, or creates our ciphertext by encryption. And we get here our decrypted plaintext. When we now change in one of the components the initialization round count only by 1, then of course it doesn't work. So you have to set up the Trivium component to use the same number of initialization rounds. Now you could ask or say, I'm interested only in the key stream, that's the Trivium cipher. generates. Can we get this also out of the Trivium component? And yes, this we can do in CrypTool 2 with every stream cipher, and there's a nice trick. You just change the input format here of your plaintext to hexadecimal, and we do the same here for the output, that we can see that it actually works. And then if you want to get the key stream, you just enter 0 bytes here, since, as you know, a stream cipher or the Trivium stream cipher just XORs the key stream onto our plaintext. So if we set our plaintext to all 0 here, we get only the key stream here, since we have no plaintext at all, or our plaintext is set to 0. And as you can see, the decryption also works very well. Yes, and this is everything I wanted to show you in this video. I first introduced you to the Trivium stream cipher of the Estream project. You now know how a single round of Trivium works, how the initialization, so putting the key and the initialization vector into the cipher works, and you know how you can encrypt and decrypt using the Trivium component in CrypTool 2. So you could now download or use CrypTool 2 for playing with the Trivium cipher if you like. So thank you very much for watching. I hope you liked the video. If yes, please give a thumbs up. Also, if you did not yet subscribe to this channel, please also do so. This really helps us to grow the channel and also to make CrypTool 2 more popular. So thank you very much for watching, and see you in the next video.